Good morning students. Today is lecture 7 of module 3. In today's lecture, we will cover about composite membranes preparation, interfacial polymerization, deep coating method and plasma polymerization. So, interfacial polymerization is one of the most important breakthrough in the inorganic membrane preparations. Deep coating is the usual and very simple technology, and plasma polymerization is also a very important technology. However, it is bit costly process, but anyway we will learn one by one about all these processes, their applications, their advantages and disadvantages. So, let us start begin our lecture today of composite membranes. So, we have discussed earlier also what is composite membrane, right. So, you can see the picture. So, composite membranes are basically asymmetric membranes having a thin dense top layer which is supported by a porous layer. Now, you can see in these pictures that there we can have either a single layer composite or we can have a multi-layer composite. So, in single layer composite, the porous substrate, there is only one porous substrate here, and the selective layer, the top layer which is doing the separation is only supported by one porous layer. But in a multi-layer composite, so we have two distinct or even more than that porous structures which are supports, right. Here you can see that below the selective layer, okay, this is the selective layer which is doing the separation. Here this is the material B and this is the material C. There are two different porous layers. Okay. The material B pore size is lesser than that of the material C. So, as we go down like this, so the pore size of the support increases. So, this is multi-layer composite. So, composite membrane is actually a breakthrough in the history of membrane technology which eliminates the low permeate rate characteristics of the dense homogeneous polymer films. So, you know, we have discussed about dense membranes which are non-porous membranes. So, there are certain applications in which we need dense membranes or non-porous membranes. However, the problem is that since these membranes do not have pores, so they suffer from very low permeate rate or permeate flux is also very less. So, the separation target is usually not met. Actually, get rid of this, the composite membrane has come into picture in which there can be a dense or non-porous top layer of having a very small thickness on the top layer followed by single or multi-layer porous structures or supports. The advantage of composite membrane is that each layer can be optimized independently. This is very important. As we have shown that this one in our previous slide, that either we can have a single layer composite or we can have a multi-layer composite. Even if we have a multi-layer composite, then also the layers are of distinct pore sizes and we can characterize and optimize them independently. So, as to obtain a particular targeted separation and to have a optimized membrane performance. So, with respect to basically selectivity, permeation rate as well as chemical and thermal stability. So, these are the parameters which actually are important for any chemical separation process. So, in the beginning composite membranes were made by separating a thin layer of very dilute polymer solution on water or mercury. So, initially when the composite membrane actually were manufactured, so it was done by, let us say there is a polymer porous structure and over which we are grafting a very thin layer of polymerous material, okay, by using water or mercury. Then it was followed by evaporation of the solvent and resulted in the formation of thin polymer. Basically what we are doing is that there is already a porous layer and over which we are casting the polymer solutions. So, in that solution the polymer which will make the top of the top layer is already soluble in the solvent. We have discussed this in our earlier lecture, how to make a polymer solvent and how the solvent evaporates. So, eventually when I cast it on the surface of the polymer support or even if it is a ceramic support also does not matter. So, after some time the solvents will start disappearing. Okay. Once the solvent evaporates, they will it will form a very thin layer of polymeric film on the support itself. Then we can go for drying or sintering, whatever process it is required to get the further and final membrane. So, usually a porous support is placed between the thin film as a support. The composite membranes are prepared by this technique had disadvantages of poor mechanical stability and was not suitable for large scale application. So, what is the problem is that if the grafting and if the fusing of the polymeric thin layer on the surface of the porous support is not proper, then during the application it will come out from the support. So, if it is not properly sticked or stitched to it, right, then the stability becomes a big problem. So, other techniques used for applying a thin top layer on the support are called interfacial polymerization, deep coating and plasma polymerization. So, to get rid of this mechanical stability problem, so interfacial polymerization, deep coating and plasma polymerization came into picture. So, such membranes having a very thin top layer along with a microporous support or even ultrafiltration support is called thin film composite membranes. So, we will discuss little about thin film composite membranes. So, these membranes are semi-permeable membranes developed primarily for desalination and water purification process. So, they are also used nowadays in batteries and fuel cells. So, there are basically we can make either two types of membranes from the thin films. So, either they will be in the nanofiltration range or they will be in the RO range. So, due to this poor range actually that is why the intended applications are mostly water desalination or water purification. So, the first viable reverse osmosis membrane was made from cellulose acetate. Okay. So, it is an integrally skinned asymmetric semi permeable membrane. You remember we discussed in our first class this membrane preparation from cellulose acetate by Loeb and Souri-Rajan is one of the most important breakthrough in membrane science, that is in University of California, Los Angeles in 1959, and they patented it in 1960. Now, the current generation of the reverse osmosis membrane materials are based on composite material patented by the Film Tech Corporation. Now, it is a part of DuPont company. So, Film Tech has initially produced such RO membrane composite membranes. So, let us closely look at this particular diagram or figure or sketch. Okay. So, you can see it is a 3-layer nanofiltration thin film composite membrane. Okay. The top layer you can see it is very thin, right. So, it is almost 150 nanometer, less than 150 nanometer. Okay. Usually polyamide is being used. The reason for using polyamide is that it will give very high rejection. Okay. And followed by 2 support layers. The first layer is the nanocomposite support, this one. Okay. It is almost close to 50 microns the pore size. So, we can use various materials, membrane materials for this, either polysulfone, polyether sulfone, polyamide, all these things, and the pore size is actually less than 1 micron. So, this is giving the support to the selective layer. So, this particular nanocomposite layer is giving the initial support to the top layer thin film membrane. Okay. Then this is the more porous structure, it is a non-woven backing. Almost approximately 120 micron. So, you can use usually polyester, there are other materials that can also be used. So, the pore size is usually greater than 3 microns. So, this is providing the major mechanical stability. Okay. So, this 3-layer configuration gives the desired properties of high rejection of undesired materials like salts, then high filtration rate and good mechanical strength. The polyamide top layer is responsible for high rejection and is chosen primarily for its permeability to water and relative permeability to water and relative impermeability to various dissolved impurities, including salt ions and other small and unfilterable molecules. So, this is another example which is a TFC thin film composite membrane, RO membrane, it is a reverse osmosis membrane. So, you can see again the top layer is polyamide. So, for the same reason polyamide is being used here. However, the structure and the support below support layers, 2 distinct support layers can be of different materials. Here it is the microporous polysulfone, okay, this layer, then followed by the reinforcing fabric. Okay. So, mostly they are of the same nature and the type. Okay. However, the thin film composite membranes also suffers from some limitations. So, 3 distinct limitations or drawbacks has been actually I am showing here. So, the first one is compaction effects under pressure. Okay. As the water pressure increases, the polymers are slightly reorganized into a tighter fitting structure that results in a lower porosity. Okay, and ultimately limiting the efficiency of the system designed to use them. So, what is happening when the process is on and inside the membrane module, due to the increase in water pressure, since the material is polymeric, so they are slightly, the matrix itself is slightly getting reorganized. So, they are getting compacted or they are getting tight, basically we can say in that word that they are getting tighter or tight fitting structure. So, what is happening? By this the permeation rate will decrease, so flux will also decrease, so efficiency of the system will be decreasing. So, in generally higher the pressure, the greater the compaction. And another problem is surface fouling. This actually comes due to colloidal particulates and bacterial infestation resulting in the biofouling characteristics of the membrane, and then chemical decomposition and oxidation. So, this all depends upon what type of solutes the particular membrane is handling. So, have a close look at this particular table. This is taken from one of the publication by Lowe et al. Okay. So, you can see this list out the commonly used monomers and some new reported monomers for this thin film membrane preparation. So, you can have piperazine, we can have MPD, which is M-phenylenediamine, then we can have PPD, we can have sulfonated carbopoly aryl ether sulfone. Then we can have DABA, DABA, people call it DABA. Okay. So, their molecular weights are also given, and then there are other materials also like trimosyl chloride, then isopothyl chloride, then we can have 5-isocyanato isophenyl chloride, and then BTEC, and there are two types of BTECs actually, biphenyl terracyl chloride. So, either MM type or OM type. So, their molecular weights are also given. So, this right hand side whatever you are seeing here. Okay. So, these are under new monomers, and at the left hand side monomers are widely used and are also used for commercial membrane preparation. So, let us now understand and learn what is interfacial polymerization. As I told you earlier that at the beginning of this particular class, that interfacial polymerization is one of the most important breakthrough in membrane preparation or membrane science and technology. So, it was first reported by Whitbaker and Morgan in 1959, long back. Okay. So, initially refers to the polycondensation of diamine and diacid chloride monomers, which reacts to form a polyamide and hydrogen chloride. So, initially the scientists who developed this, they call this a polycondensation reaction. So, one diamine amine, basically amine, and another acid chloride monomer are fused together or are reacted together. So, they form a polyamide and a hydrogen chloride once after the reaction. So, when compared with bulk polymerization, interfacial polymerization exhibits great flexibility in surface topology and chemical properties of the prepared functional materials. So, to date, interfacial polymerization has evolved as a robust and effective approach to synthesize a wide range of functional polymer materials. So, many different types of polymeric materials can be used for interfacial polymerization, and various types of membrane materials of different grades and sizes can be prepared. So, using interfacial polymerization, various monomers can be utilized to fabricate various polymer materials with unique topological and chemical properties such as anisotropic shapes, hollow fiber, hollow cores, or alternative surface chemistry. So, let us now understand what are the different types of fabrication systems that is already in practice for interfacial polymerization. You can closely look at this particular figure given in the right hand side. So, this figure is based on liquid solid, liquid liquid, and liquid in liquid emulsion interfaces. So, interfacial polymerization can take place either on one side or on both sides depending on whether the monomers are present in one or both immiscible liquid phases. Okay. So, when the monomer only exists in a single liquid phase and the initiator are dissolved in other liquid phase, they polymerize into homogeneous polymeric material at the interface. Okay. So, the interface is very important, and at the interface only polymerization is happening. Composite polymer materials are obtained when the two monomers separately dissolved immiscible liquids polymerize at the interface. Now, let us say what are the different types of fabrication system. So, we can have a liquid in monomer and solid system. Okay. So, this is the interface actually which I am talking about, the reaction is taking place there. Then we can have under liquid liquid system, we can have liquid in monomer and liquid system, or we can have liquid monomer and liquid monomer systems, both are same. Then we can have liquid in liquid system, where we can have a liquid in monomer system, or we can have a liquid in monomer in a liquid system. Okay. So, these are basically this, and these are emulsion type of interfaces. Okay. So, you can see the globules, you can see here the globules here and here. So, these are actually emulsions. in a liquid solid interface, polymerization begins at the interface and results in a polymer attached to the surface of the solid phase. So, this is a solid interface. So, let us say I have a polymeric support material, solid material, over which I will try to carry out the polymerization reaction. So, I will pour my desired this one amine as well as the acid chloride on the surface of this particular solid support, and the reaction will happen at the liquid and solid interface. That means the polymerization reaction. So, that is how it happens in a liquid solid interface, whereas in a liquid and liquid interface with monomer dissolved in one phase, polymerization occurs only on one side of the interface, whereas in liquid interfaces with monomer dissolved in both the phases, polymerization occurs on both sides. Okay. So, an interfacial polymerization reaction may proceed either stirred or unstirred. So, we can either stir the process or we do not need a stirring at all. So, in a stirred reaction, two phases are combined using vigorous agitation, resulting in a higher interfacial area and a higher polymeric heat. Always stirring is a better solution for achieving a better result, whether it is a mass transfer or whether it is a reaction, and most interfacial polymerization are synthesized on a porous support in order to provide additional mechanical strength. That is what actually TFCs are mostly the interfacial polymerization happening with liquid solid interface. That is what it is telling. It is easy to carry out, and the solid porous material is already providing a mechanical support, okay, to the thin film that is going to be developed at the interface. So, let us try to understand now how the process happens. Two reactive monomers, or we can have one pre-polymer, undergoes polymerization reaction at the interface of two immersible solvents. Okay. So, you can see the first one is that this is a porous support membrane, okay, and this is the interface on which we are talking about that our reaction will take place. So, the support layer, which is generally an ultrafiltration or microfiltration membrane. So, which one to choose, that is depending upon what is the intended application. So, you can either go for a ultrafiltration membrane as a support, or we can go for a microfiltration membrane as a support. So, this membrane or porous support is immersed in an aqueous solution containing a reactive monomer or a pre-polymer, normally of the amine type. So, either we can usually have a amine type. So, once you immerse, then the amine actually get inside the pores, you can see from here, right. The film is then immersed in a second bath. Okay. We are going for a second bath containing a immiscible solvent in which another reactive monomer, often an acid chloride, has been dissolved. So, basically what we are doing, we are taking an amine solution and putting it inside that amine solution, we are dipping our membrane support, either it is a ultrafiltration or microfiltration. Then once it is done, the pores are filled with this amine, then we take it out and then put it in another bath which is having a immiscible solvent, and in that the diacid chloride or acid chloride, whatever it is already dissolved in. Okay. So, you can see now this is a non-aqueous medium which is getting in contact with the polymeric support already containing the amine solution inside its pore. So, these two reactive monomers, that is amine and acid chloride, react with each other to form a dense polymeric layer. So, the reaction is proceeding here, then we can get a dense polymeric layer here. Okay. So, it is a very thin layer we obtain from this method. So, this can be done in a lab scale also. Only you have to be very careful that what are the solvents you are choosing and what is the amine and what is the acid chloride that you are choosing, and you have to do it very carefully, okay, so that the thickness of the membrane that is finally is coming out should be thin, so that there will be a proper separation. So, heat treatment is often applied to complete the interfacial reaction and to cross-link the water soluble monomer or pre-polymer. So, usually once it is the polymerization is over, it is not the end of the process, then the membrane is taken out, dried, and it goes for a further this was heat treatment, okay, either in a dry chamber or it can be sintered at a particular desired temperature. So, that this one the water soluble monomer or pre-polymer will get cross linked. The advantage of interfacial polymerization is that the reaction is self inhibiting, okay, through passage of a limited supply of reactants through the already formed layer, resulting in an extremely thin film thickness with almost 50 nanometer range. So, these are some of the examples of the preparation of the composite membranes by interfacial polymerization. The amine is the aqueous phase. Here the aqueous phase, these are all amines, you can see the NH containing group. Then the acid chloride or isocyanide is in the organic phase. So, the first one is the aqueous phase, which is containing the amine. The second is the organic phase, which is containing either the acid chloride or a isocyanate. It can be anything else also, depending upon what type of membrane you want to actually prepare. Okay. And then resultant is the product, this is the polymerization product. Interfacial polymerization reactions generally result in fast polymer chain growth and polymer precipitation at the liquid-liquid interface. Okay, so, it is a very fast instantaneous reaction, and you know that it does not need anything to start the reaction, it is a self starting reaction basically. The properties of the polymers depends on a large number of parameters, we will see it in the next slide. So, polymer properties such as molecular weight, polydispersity, degree of branching or cross linking, thickness, density, layer roughness, etc. play a very important role. So, the parameters listed under table 1 are strongly interdependent. For example, the solvent miscibility and viscosity influences the monomer diffusivity and solubility in the opposite phase. Stirring, addition of a surfactant or temperature influences the solubility as well. If you stir it and or add some surfactant, okay, or even you go for certain temperature application, okay, then it will affect the solubility. Similarly, the concentration, reactivity, stoichiometry, solvent pH and removal of reaction products influences the polymer growth rate. So, this table I was referring to. So, this is the summary of synthesis parameters that determine the nature of the polymer formation during the interfacial polymerization. Okay. So, solubility in the opposite phase, diffusivity, okay, concentration, reactivity, stoichiometry and purity for the monomers, and similarly the solubility limit, permeability for monomers, growth rate of the polymer, and if we use any surfactants then its type and concentration, and the solvents characteristics features like pH, viscosity, miscibility and the conditions. If we are carrying out the reaction under an ambient atmosphere temperature, or we are heating it, we are stirring it, what is the time, residence time we are allowing, and what is the product that is forming, and are we scavenging it. So, depending on the types of product will form, either monomer distributed over interface, or extent of the film growth will take place, or film growth rate will be very faster, and side product formation, okay, will take place. So, different applications of interfacial polymerization includes for synthesizing conducting polymers for electronics, such as chemical sensors, fuel cells, supercapacitors and nanoswitches. For example, PANI. So, it is used to prepare nanofibers. Then PPY coated ordered mesoporous carbon for fuel cell application. PPY is polypyrrole, and then it is also used for separation and purification membranes, as for example, RO membrane preparation. Other applications are in drug delivery systems, cargo loading micro and nano capsules, which are already in practice and commercialized also. Students, the next method that we are going to discuss is deep coating. This is one of the most easy, simplest method, and it is a crude method also. Now, in a crude way, basically we can do it in lab scale, we have done it in many times, and it is very easy to do. However, in the industry it is done using of course different machines. So, composite membrane with a very thin and dense top layer can be obtained by this simple and useful deep coating technique. Now, membranes obtained by this method are used in reverse osmosis, gas separation and pervaporation. An asymmetric membrane, hollow fiber or flat sheet, either you can use hollow fiber or flat sheet membrane, does not matter, okay, often of the type used in ultrafiltration, is immersed in the coating solution containing the polymer, prepolymer or monomer. Now, you can see this scheme. So, we have a dry asymmetric hollow fiber or flat membrane, okay. I am putting it inside a coating bath, okay. So, this bath actually is containing the material, it can be prepolymer, polymer or monomer, which we actually want to coat over the surface of the hollow fiber or flat membrane, okay. Once it is dipping, so dipped, then you can take it out slowly, okay, then it goes to the oven for the drying, and then we get a composite membrane. So, the concentration of the solute in the solution being low, often less than 1% actually, when the asymmetric membrane is removed from the bath containing the coating material and the solvent, a thin layer of solution adheres to it. Okay. So, actually you can see this particular example or the figure, you can see the stages of deep coating processing. So, initially the dipping of the substrate into the coating solution. So, you are dipping it. So, slowly you are putting it inside the bath, which contains the polymer, prepolymer or your this one monomer, okay. then you allow it some residence time basically, so that the coating actually happens properly, then you take it out slowly in this way, right. So, you can do it in hand, we have done it, okay. It is very easy to do it, only thing is that you have to dip it slowly and further slowly you have to dip out, okay. And once it is done, you can see that it comes out of this one, then if you allow it, okay, then what will happen is that in the ambience only the solvent will evaporate, see these are the solvent evaporation happening, okay, and then cross linking starts, right. So, such cross linking leads to a thin layer becoming fixed to the porous sublayer. So, cross linking is often necessary because the coated layer has no mechanical or chemical stability itself, or its separation performance is not sufficiently high in the uncross linked stain. If see, basically we are talking about cross linking, if it is not cross linked, the layer which is attached or coated on the surface of the polymeric membrane, or even let us talk about a ceramic membrane, it will come out during the application, okay. So, one of the most important advantage of deep coating is its ability to provide complete coverage to the substrate with challenging geometries. So, if we have a very different types of geometries, or let us say I have a geometry something like this, okay. So, as tubular structures, okay. So, how do I prepare a thin film membrane? Okay. So, deep coating is the only way. So, entire this material I can put it in the bath, so it will get coated, then I take it, okay, and I can go for the solvent evaporation, cross linking, some heat treatment or whatever it is. So, the entire substrate material is covered by this process. The interesting part of deep coating is that by choosing an appropriate viscosity, the coating thickness can be varied with high precision from 20 nanometer to 15 micron while maintaining high optical quality. So, you have to choose a appropriate viscosity of the coating material. So, if it is a very low viscous material or the solvent, then what will happen, that film will be very thin, and the chances of it coming out during the application is also more. So, you have to decide the thickness, there is no thumb rule, basically you have to prepare certain, you have to optimize it doing some experiment only, you have to prepare 10 or 15 membranes with different viscosities, and you will find that one particular viscosity suits your particular application. This is how actually it is done in lab and also in commercial scale before we go for a full fledged production. If reactive systems are chosen for coating, as it is the case of a sol gel type of coating like alkoxoids or pre-hydrolyzed system, the control of the atmosphere is indispensable. The atmosphere controls the evaporation of the solvent, and the subsequent destabilization of the salts by solvent evaporation leads to a gelation process. A transparent film is also formed due to the small particle size in sol. So, you can see this particular figure. So, this is the gelation process during deep coating, okay, obtained by evaporation of the solvent and subsequent destabilization of the sol. So, particle size of the sol plays a very important role here, okay. So, you can see two scanning electron microscope images, okay, of a composite hollow fiber membrane with a polyetheramide sublayer, okay, and a polydimethyl siloxane top layer. So, this is polyetheramide this one, and this is polydimethyl siloxane top layer, okay. The sublayer is a hollow fiber of polytheramide obtained by immersion precipitation, in which a thin layer of polydimethyl siloxane was deposited by a deep coating procedure, okay. Cross linking of the dimethyl siloxane was achieved by heat treatment, and a very thin top layer of about 1 micron can be applied via this technique. The ultimate coating thickness can be described by solution hydrodynamics. An equilibrium thickness is obtained after a certain period of withdrawal of the fiber and sheet that form the solution, in which the gravity forces and drag forces are balanced. You please see this particular figure where you can see the direction of withdrawal, okay. This is actually the support of the substrate, okay. Here the polymer solution is there. So, I have dipped it, then I am taking it out slowly, right. So, this is the direction of the withdrawal you can see, and the polymer concentration profile actually happens like this, it is falling like this, okay. And whatever the thickness is that is getting resultant, that is called the equilibrium thickness. The final thickness is the result of various forces that are acting. So, viscous forces basically. So, capillary forces and inertial forces, okay. It is only not the viscous forces, but the capillary and inertial forces also plays an important role. The coating process can be described by the Navier-Stokes equation, which finally result in an equation for the final thickness of the coating layer. So, you can see this equation, H infinity is 2 by 3, eta V by rho g under root. So, H infinity is the equilibrium thickness, V is the coating velocity, rho is the density, and this is the viscosity. Okay. And after evaporation of the solvent, and thin polymer film is formed at the surface with thickness proportional to volume fraction of polymer in the solution. Although the method itself is experimental, rather simple to carry out, there are number of points that should also be emphasized. So, the first one is the state of the polymer. So, one of the most important features in the solution coating process, what is the type of polymer basically? If the polymer is an elastomer, okay, then a thin defect free layer can mostly be obtained. Mostly elastomers are used to get a very thin and a defect free layer. If the polymer is glassy, then glass transition temperature is passed at a certain moment during the evaporation process, and upon further evaporation large forces may be generated, and this may result in defects and subsequently and consequently in leakages. So, cracks will develop, right. Second one is pore penetration. So, if a porous support is used, pore penetration will occur during the deep coating process due to the capillary forces. Especially in the case of glassy polymers, the support may then exhibit an extremely high resistance to mass transfer, although the layer that may have been penetrated into the pores reaches a thickness of 1 or few microns. So, actually what is happening, pore penetration is good or also bad also. Why it is good? Because then the linking or the sticking of the material or the thin layer over the surface of the support will be better, because it has penetrated into the pores. So, the support will be more. However, it is blocking the pores of the support also, thereby restricting the free flow of the material which is separated by the top layer. Okay. So, the most versatile method to avoid or reduce pore penetration is pre-filling of the pores, so which prevents the solution. So, what is being done is that, so when you are taking the support, you pre-fill the pores of this support using some solvent which can later be evaporated or been taken out through the opposite side of the membrane. So, that once the pores are filled, then nothing will get inside the pores once again. So, there will be no more pore penetration basically. So, other methods that can be applied are a high molecular weight and employment of a good solvent, since both parameters increase the hydrodynamic radius of the polymer coil in the solution. So, what is the molecular weight you are using? If the molecular weight is very high, then it is favorable. Okay. A high molecular weight does increase the viscosity as well, that is also very important. And another important factor in this aspect is the pore size distribution of the substrate, which should be narrow as possible. So, on the other hand, surface porosity must be high. A well performed characterization of the support layers is essential for the proper selection. Then comes the non-wetting liquids, the importance of the non-wetting liquids. So, if the solvent of the coating solution does not wet the porous substrate, no pore penetration will occur. This method can be applied to coat porous hydrophobic polymers such as polyethylene, polypropylene, polytetrafluoroethylene or PVDF with a water soluble polymer. Now, since water does not wet the membrane, okay, or at least if the Laplace pressure is not exceeded, then the polymer will definitely not penetrate. So, the solution properties are very important and is determined by 4 parameters. So, those are type of polymer, type of solvent, polymer concentration and molecular weight. So, the polymer which is assumed to be linear and amorphous occurs in solution as a random coil, and the dimension of the coil depend on the type of solvent. In good solvents the coil dimensions are large, whereas in poor solvents the coil dimensions are very smaller. If the solvent is very poor, then the coils aggregate and precipitation may occur. So, that is another thing that has to be actually taken care of. The quality of the solvent can be expressed by the Flory-Huggins interaction parameter X. If the polymer concentration increases, then the coil will overlap, that is another problem. So, this process always occur in deep coating where the solvent is being evaporated, and at a certain moment the coils will overlap and will form an entangled network. The formation and morphology of the network strongly depend on the solvent and the polymer. An important property is the state of the polymer that we just discussed. If it is a elastomer, and what will happen if it is a glassy polymer, then what may happen. Elastomers are good film formers, and during the coating process the polymer remains in the rubbery state. On the other hand, glassy polymers pass at a certain concentration the transition from rubbery state to glassy state. So, when that transition is happening, so certain temperature we are applying, so that may result in some crack formation. So, at that moment the mobility of the polymeric chains have been reduced drastically, often the material is not able to compensate the stress built up due to evaporation, and this may result in failure. So, the tensile strength of the polymer may be increased by increasing the molecular weight, and especially for the intrinsically brittle polymers this is even a requirement. Various application of deep coating includes plate glass, solar energy control system, anti-reflecting coating for windows, optical coating on bulbs, optical filters or dielectric mirrors, fabricating multi-layer systems with up to 30 or 40 coating with very high precision. So, the students, the next process of preparing thin film membranes is plasma polymerization. So, plasma polymerization is a special means of preparing an ultra thin film of unique polymers retaining many of the bulk properties of the polymer such as permeability, electric volume resistivity and dielectric constant. Now, plasma polymerization may be plasma induced polymerization or plasma state polymerization, either of these one type will be used. So, technically it follows the free radical polymerization concept, and conventionally it is similar to the free radical polymerization of molecules having unsaturated carbon-carbon bond. Now, let us see how it happens. So, the general intention is to produce ultra thin and pinhole free polymer layers. So, no defect actually, we do not want any defective layer here, and thin polymeric layers of variable composition, okay, with well defined and regular structure, that is what actually we want. Then it produces polymers that are durable and resistant towards aging, oxidation and shrinking. And now you can see how the formation of polymer layer through plasma polymerization is happening. So, the ideal condition would be the polymer and then plasma polymer layer deposition happening like this, but actually in real it never happens like this. So, you can see because the monomer molecules are available in this type of form. So, when it is getting deposited using the plasma, so they deposited something like this. Okay, it is a random structure basically, it is not a very planned structure. So, the plasma is obtained by the ionization of a gas by means of an electric discharge at high frequencies up to 10 megahertz. Two types of plasma reactors are used. In one type the electrodes are located inside the reactor, okay. In another one the electrodes or the coils are located outside the reactor. In a plasma polymerization reactor with the discharge coil outside the reactor is also called the electrode-less glow discharge, okay, if it is outside. Many book you will find this particular topic, okay. The pressure in the reactor is maintained between 10 to 10 to the power 3 Pascal, okay. You can see the sketches of the plasma polymerization apparatus. On entering the reactor, the gas is ionized, and by ensuring that the reactants are supplied separately to the reactor, all kinds of radicals will be formed through collisions with the ionized gas, which are capable of reacting with each other. So, the resulting product will precipitate on a membrane, okay, when their molecular weight becomes too high. So, this is a bell jar type of system, and this is another reactor, okay. Here the discharge coil is located outside, okay. Here the discharge coil is also located outside, but electrode is little pushed here, okay. So, what is happening here, this is the membrane, okay. Here the porous film or the membrane is located. Then when the ionization taking place, the monomer is ionized, and actually they are this one coming and depositing on the surface of this particular membrane, okay. So, they are flowing like this, right, and the coating or the deposition should be uniform, otherwise we will get a various thickness membrane. So, the flow control of gas as well as that of monomer is very crucial in the plasma polymerization apparatus. A very thin layer of thickness almost 50 nanometer can be obtained, provided the concentration of the monomer in the reactor is carefully monitored to control the thickness. This is what I was talking about. If this is not been taken care, now what will happen? So, let us see, this is the porous support over which you are having a thin layer deposition. So, what will happen? Here the thickness is very less, here the thickness is more, here the thickness is different. So, it should not happen, it should be uniform, okay. So, other factors important in controlling the thickness are polymerization time, vacuum pressure, gas flow, gas pressure and frequency. So, these are, you can see that there are so many parameters which actually eventually decide the thickness of the layer. So, the structure of the resulting polymer is generally difficult to control and is often highly cross linked. Let us understand the mechanism. Actually, the mechanism of plasma polymerization is very complex. The high energy ionization which takes place in the plasma system, so breaks the precursors into various ions, free electrons, radicals and natural fragments, all of which can be involved in the recombination of these fragments into plasma polymers on the surface of the substrate. So, that means in various forms the plasma system as a precursor is being deposited on the surface of the support. So, the exact chemistry of the resulting coating is dependent on the chemistry of the precursor along with a host of parameters specific to the plasma deposition system. So, this deposition system can be the chamber design, electrode configuration, the RF frequency and the low pressure and flow rate of the precursor. So, many things that actually finally deciding upon. Actually, it is very complex, the mechanism. The reason is that the precursor is getting fragmented into various types of things. It may be ions, it may be free electrons, radicals and some neutral fragments. So, that is the reason why the mechanism is very complex. So, student, this is one of the plasma polymerization mechanism. You can see this is the polymer substrate, how it looks like. This is the monomer. Okay. This monomer is getting divided into various types of ions, okay, and free radicals. Then when they polymerized, okay, so we will get something like this cross linking shape, right. So, we can have either electrons, ions, radicals, UV, all these things, all of them are getting deposited on the surface, and then once they are depositing, they are getting cross linked. So, the most expensive studies of plasma polymerized membranes were performed in the 1970s and 80s by Yasuda, who tried to develop high performance RO membrane by depositing plasma films onto microporous polysulfide films, right. So, long back it was done, that is not a very new technique that is developed, but the only problem with this is that this is a very costly process, and more recently other works also studied have studied gas permeability of plasma polymerized films. Okay. For example, Stanson and Spencer were able to obtain a gas permeation plasma membrane with a hydrogen methane selectivity of almost 300. You can imagine the very high selectivity to separate hydrogen and methane. Then Kawakami et al. Have recently reported plasma membranes with an oxygen nitrogen selectivity of 5.8. So, this selectivity is compared to less than, but still with respect to oxygen and nitrogen it is very high. Please try to understand that oxygen nitrogen both are getting separated from the air. Okay. So, both selectivities are good compared to those of other membranes, and the plasma films were also very thin. So, the advantages of plasma polymerization is its ability to produce polymer films of organic compounds that do not polymerize under normal chemical polymerization condition. So, students try to understand that there are certain polymers which we are having very good property to form a particular membrane. However, they are not getting polymerized under standard reaction conditions or other processes. That is why a plasma polymerization helps. So, most of the monomers, even saturated hydrocarbons and organic compounds that do not have a polymerizable structure can be polymerized by using this technique. So, this is the beauty of this particular process. A number of steps involved in coating a substrate with conventional polymers can be avoided in plasma polymerization that require a single step for coating. It is a green process. So, you need to understand that it is a green process, as there is no solvent is being used. However, and no cleaning of the resultant polymer is also needed. It is almost getting cross linked during the process. Okay, then you just take it out, just leave it for some time for air dry. That is the finished membrane basically. Okay. Only the cost of energy involved is very high, and disadvantage is the high cost of the process. This is the most important thing actually. Complex process, the mechanism is very ill understood and difficult to control the chemical composition of the surface after modification. Once it is done, you cannot do any modification, and the complexity of the process also makes it impossible to theorize what the resultant polymer will look like or unlike the conventional process, which can be easily determined based on the monomer. Okay. So, if I know what is the monomer that I am going to deposit on the surface of a support in other processes like interfacial polymerization, deep coating, I can predict what type of layer that will be deposited on the surface of the support, but I cannot predict that, at least even theoretically during plasma polymerization, because the ionization is making the monomer or fragmenting the monomer into various different types of ions, and this one radicals and UV also. So, different applications are adhesion, composite material, protective coating, printing, biomedical applications, water purification, dielectric materials such as sensor production. So, students, please refer to these books. This I am showing you in every after every class. So, Mulder is the most important book that I am referring for. So, you can refer other books also as a reference or text for this particular subject. So, students, next class we will try to understand and learn one of the most important breakthrough in membrane separation or membrane preparation technique, which is called the sol gel process. Then we will try to understand how ceramic membrane can be prepared. I will show you also how you can prepare ceramic membrane in lab scale, and then we will discuss about membrane modification also. So, thank you very much. So, in case you have any query, do write to me at kmohanty@iitg.ac.in, and I will definitely reply to your queries. Thank you very much.